Okay, now we're on circles. We know a little bit about circles, so we're going to have a little bit of a review, but this should already be standard knowledge. I do have some precise definitions, though, because I know that everyone knows what a circle looks like. I know that you guys know what shape it is, but sometimes you don't really know the pure definition. So if you think about it, a circle is a set of points in a plane that are all given distance from a point on the plane. Let's explain that real quick, just so you can visualize. This circle is made up of infinite number of points along the edge of the circle, correct? Every single one of these points is equidistant to the center. Every single one of these. These are all congruent lengths. They're all equidistant. They're all radii. But that is the definition of a circle. It's a set of points that are all equidistant from the center. That's a circle. Okay? So, with that in mind, we do know that, of course, the given point that they're talking about is the center, and the given distance is the radius. And of course, you guys should remember that a radius is just a segment that joins the center to a point on the circle. Okay? And if it's plural, it's called radii. All right. Now, let's continue with some more definitions. Very simple definitions, but still very important. When you have two or more coplanar circles that have the same center, they're called concentric circles. So these are circles that share or have the same exact center. Now my drawing, it's not exactly perfect, but I did the best that I can. So it is a little bit off. That truly isn't really concentric, but you get the point. Okay, two circles that share the same center. Okay, this guy and this guy, they're sharing that center. So you got concentric circles. Now, two circles are congruent if they have congruent radii. Think about it. Radii is what determines the circumference and the area of a circle. So if they have the same radii, they're going to be congruent circles. Okay? Yes, sir. If they have congruent radii, they're congruent circles. If they have congruent radii, let's say the radii is 3 and 2 circles. They're going to have the same circumference. They're going to have the same area. So therefore, they're congruent circles. Okay? Now, sometimes you're going to have word problems or proofs or situations where they're talking about points that are inside, outside, or on the circle. I know that it's pretty standard. You guys know what inside and outside and on mean. But let me just go ahead and make sure that you understand the true definition of this, please. A point is inside, in other words, in the interior of a circle, if its distance from the center is less than the radius. So if the radius is, let's say, 10, but OA is 8, even if they tried to manipulate the circle to try to confuse you, just by knowing that the radius is 10 and OA is 8, A is inside. It's an interior point. Yes, sir. How would they try to confuse us is the question. They could do another circle like this. They could try to do that. Or they could draw this, put it here like this, do another one here like this, put an N here. Say the radius of circle N is blank. AN is blank. Is A an interior point of circle N? That's one way, okay? Now remember, in the diagram, remember guys, In the diagram, they are not going to always have beautiful, pretty, nice little points that are perfectly symmetrical and drawn to scale. In fact, most of the time it will not be drawn to scale. Most of the time on the SAT, it's amazing actually. I've seen questions where you're calculating sides and this side will be 5 and this side will be 18. That makes no sense. But if you think about it, on the test we just did, wasn't that the way the bottom worked out? Yeah, you had 2 and 6 and it did not look correct. You do not always draw to scale. Yes, sir.
Could they make 08 like 12 and radius 10, even though 8 looks like it's a circle but it's not?
The question is, could they make OA 12 and then they said the radius is 10? Yes, if they did that, then that would mean that A is an exterior point, which is the one we're going to now. Thank you, Alec. Very good. If they drew it inside, you go by the numbers, not by the figure. You go by the numbers, not the figure. Because think about it. It's impossible. Yes and no. They will tell you this is not drawn to scale. This is impossible for that to be 5 and that to be 28 from our bird's eye view of it. But I am telling you, it's not drawn to scale. So if they tell you that, the figure pretty much means nothing. You got to go by the numbers always. There's an old saying, it's called proof is in the pudding. All right? Absolutely. If we were building something, son, that figure that I just erased, yeah, that would be impossible. 28 is going to be longer than 5. But you always got to be aware that a lot of times things are not drawn to scale. So, if a point is outside or in the exterior of a circle, its distance, from the center is greater than the radius. So in this case, maybe the radius is 12, but I tell you that OC is 15. We know by fact, there's no question to it, OC is 15, it's greater than the radius. That means C has to be outside of the circle, in the exterior of the circle. And then of course, a point is on the circle if the distance from that point to the center is equal to the radius. Then it is a radius. Okay? Does that make sense, gentlemen? Okay. So we have the points interior, exterior, and on the circle. All of them very important. Okay. All right. Now, chords and diameter. Guys, if you guys didn't get that all, I'm sorry. Remember, I do put the PDF up, and I do put the video up. Points on a circle can be connected by segments called chords. If that chord happens to go through the diameter, through the center, then it is a diameter, okay? So a diameter is a chord, but a chord is not a diameter. All right, and that we knew as well. So chords and diameters, very simple. Now, circumference. Circumference, I put in parentheses here, is the perimeter of a circle. Perimeter, by definition, is the sum of all sides of a polygon. But circles aren't polygons, and circles do not have sides. So they came up with the word circumference. Okay? And circumference means the distance around a circle. So in other words, it's the perimeter around a circle. And it is circumference equals 2 times pi times r, or diameter pi. If they ask you to calculate the circumference of a circle in terms of pi, then that means, let's say the radius was 12, then it'd be 24 pi. If they tell you to round to the nearest, whatever, tenths or hundredths, then you use the pi key in your calculator, or you use 3.14, and you can find the actual value. Okay? Area. Area, same for circles as any other figure. How many square units are inside of the figure? Remember, if I tell you that my house is 1,200 square feet, that means that I can put 1,200 squares that are 1 foot by 1 foot. We are clear with the whole concept of area, right? I made sure that we went over that in detail. It's how many square units inside of that figure or object or that space. Okay? And area equals pi r squared, of course. And again, pi could be pi symbol. If they tell you find the area in terms of pi, if they say find the area rounded to the blank, to the tenths or the hundredths, then you have to use 3.14. Yes, sir.
Shape is like house when they do the area. Like, does it depend?
The question was, what shape was the house when they do the square footage? It's actually they measure the foundation. Your house is built on a foundation. Now, of course, not all houses are just squares, right? A lot of houses, they come out, or they'll have an extension over here. So they draw it out. And they break it up literally into rectangles and squares, and sometimes triangles. Maybe you have a triangular area here where you have like a pool. So whatever shapes they have, they combine it, and we're going to be doing a lot of that work soon. We're going to be finding areas of blueprints. But that's the question was, how do you find the square footage? They go by the actual foundation. Yes, sir. Yes, sir? Okay, that's a great question. I'm so glad you asked that. How did they come up with pi? How come it works for all circles? Okay. Back in the day, the Greeks were really bored. They didn't have YouTube or anything like that. So they had to be forced to use their brain. And what happened was they came up with, or they didn't come up with, they noticed the following. Whenever you have a diameter of any circle, okay, that circle's diameter, you can technically 100% wrap it around the circle 1, 2, 3 full times, and this little leftover piece is the 0.14 because you know that pi is irrational. So that's what pi is. Pi is basically telling you, hey, the diameter can be wrapped around this circle 3 full times, and that little bit left over. That's why we got the 3.14, and it really continues forever. It's an irrational number. Thank you, son. That's a great question. Does that make sense? That's how pi came up. No, that explains pi. That doesn't explain circumference. That explains pi. How does pi r squared give you the area? They came up with that formula a long time ago. If you want, we can go over the proof one day, but it's a little bit lengthy. Yes, sir. Okay. The question was, if pi is a set distance, it's not a distance, first of all. It's a value. And it is not a set value. It is an irrational number. So it keeps going on forever. But since they use this as a uniformed measurement, they went ahead and rounded to the hundredths place, which is 3.14. Okay. So, circumference, area. Good. Okay, now, radius-chord relationships. We're going to be working with this concept here, guys, and you're going to see how this all comes together with a few theorems that we're going to prove. It's called the radius-chord relationships. And the radius-chord relationships, the distance from the center of a circle to a chord is the measure of the perpendicular segment from the center to the chord. So if they ever say to you, find the distance from the center to the chord, you're going to be looking for the distance of the segment that is perpendicular to that chord. We're going to prove all of this in a second, okay? But that's when they ask you on an SAT, on my test, on a homework, find the distance of OP in this case. Well, you better darn sure make sure that OP is perpendicular to AB. They never want the distance to be like, let's say, this. They will not accept that as the distance from the center to the chord. They don't want this one. They don't want this one. The distance from the center to the chord will always be the segment that is perpendicular to that chord. Not also the midpoint. No, not necessarily. It is the measure of the perpendicular segment to the chord. And we're going to prove things later, so relax.
When it's perpendicular, it is.
We're going to prove things, so I'm ignoring your questions. Okay,
Then you see the video.
next. We move on. We move on. Now, Theorem 74. If a radius is perpendicular to a chord, then it bisects the chord. But I did not want you to confuse the two, son. This does not say that the center has to be the perpendicular bisector. It is just saying that when you're looking for the distance from the center to the chord, it is the distance of the segment that is perpendicular to that chord. Now, knowing that, yes, you're 100% right. If you're given circle O, and they tell you that OD is perpendicular to AB, well, then this is easy to prove that OD bisects AB. OA and OB are congruent because all radii of the same circle are congruent. Okay? I didn't say anything and you're telling me no yet already. Reflexive property here is OE. So triangle OEA is congruent to triangle OEB because of HL. And then because of HL, we know the congruent, so AE is congruent to EB because of CB/CTC. So that is why this theorem is valid and works. Okay? Now, Theorem 75. All right. I messed up here, and I apologize. Let me just draw this out here, because we don't know that yet. Okay, so we have circle O again. I'm sorry, let's read the theorem. If a radius of a circle bisects the chord that is not a diameter, then it is perpendicular to that chord. It's the reverse. It's the converse of what we just did. So let's think about this. We know that AE is congruent to EB already, correct? Don't we know that AO is congruent to AB because all radii of the same circle are congruent? Okay, so how would AO and OB? So how would we know then? How do we prove that that is perpendicular? How do we prove that? Who remembers? No, you don't do side, side, side. All side, side, side is going to prove to you is that they're both congruent. That does not prove that that's going to be a 90. Yeah, but it's going to be long. You'd have to then prove that AEO is supplementary to BEO. Then you'd have to prove that if angles are congruent because of CB/CTC and supplementary, then they're 90. Then you could prove it that way. But that's a mission. Thank you. You can do the equidistance theorem. Think about it, guys. Remember what it said. If the endpoints of a segment are equidistant to 2 points, those 2 points create a perpendicular bisector. A and B are equidistant to O and equidistant to E. So therefore, OE is the perpendicular bisector of AB. So that's the equidistant theorem. Remember that geometry always builds on itself. Right? Last theorem. Theorem 76. Says that the perpendicular bisector of a chord passes through the center of a circle. Now this one's common sense. According to the equidistance theorem, okay, it states that you create a perpendicular bisector when the endpoints are equidistant to the 2 points that create the perpendicular bisector. So since this is a line, aren't there infinite points in a line? It keeps going on forever, correct? So that means it's going to continue going till it hits here. Once it hits O, isn't AO and BO, aren't they congruent? Aren't AE and BE congruent? So B is equidistant to E, and A is equidistant to E, and A is equidistant to O, and B is equidistant to O. So it'll be the equidistance theorem again. Does that make sense? Yes, sir. I'm sorry, can you repeat that, please? Where do I get line OE? I don't have a line OE. I started with DE, which has an arrow, so that means it continues on forever, sir. And it will be the perpendicular bisector because, look, at this point, isn't B equidistant to this point and also to E? At this point, don't I still have the equidistant? Once I get to the final center, don't I still have the equidistant? So it doesn't matter how far up segment DE goes, it's always going to be a perpendicular bisector to the AB because B and A are going to be equidistant to that point, that point, that point, and that point. So it doesn't matter the height. Okay, now, problem 1. Given circle Q, they tell you that also PR is perpendicular to ST. Now, I have, like I said, circle Q, and PR is perpendicular to ST. I want to prove that PS is congruent to PT. Now, first things first, the givens. Very good. You got circle Q, and that PR is perpendicular to ST. Now, I know that in the past, we are very trained to say, oh, okay, PRS and angle PRT are right angles. If you said that, that would be correct. But we're elevating our thought process now. We don't need to prove that that's a right angle. Where do we go from here? Where do we go from the fact that PR is perpendicular to ST? What do we do? Use those theorems. That's what I'm talking about. That's what I'm talking about. Great job. He said that PR bisects ST. Of course. If a radius is perpendicular to a chord, it bisects that chord. They told you that it was perpendicular already, so you didn't have to state that angle PRS and angle PRT are right angles. No. Just knowing that it's perpendicular is enough to activate the theorem. If the radius is perpendicular to the chord, then it bisects the chord. And there you go. Okay? Now, where else do we go from here? Yes, sir? No, I wouldn't. I wouldn't do that. I would say that PR bisect is the perpendicular bisector then of ST. Oh, wrong one. Oh, epic fail. The combination of 1 and 2, if it's perpendicular and it's a bisector, then it's a perpendicular bisector. And then I ruined it already. The proof is that PS is congruent to PT because of the equidistance formula. Okay? Look, if PS, okay, since PR is perpendicular bisector to ST, doesn't that mean that T and S are equidistant to both P and R? So, because of the equidistance theorem, PS must be congruent to PT. Yes, sir? Okay, the question was, couldn't you have done PR to PR reflexive? Then you would have said PRS is congruent to PRT because of side angle side. Then it would have been side angle side. Then PS would have been congruent to PT because of CBC to C. The answer is, could we have? Yes. But why would you want to? I can get from point A to B in a straight line. But I can also go around point B 72 times. We're trying to look for the quickest, most accurate way to get there. But the answer to your question, son, is yes. And I would not have marked that wrong. The question is, will you have enough time to work that out? Okay? Thank you, son. Way to think, though. I'm very proud of you. Next, easy one. The radius of circle O is 13. The length of the chord PQ is 10. Find the distance from chord PQ to center O. Remember, guys, the distance, remember, is always the perpendicular segment from the center to the chord. You with me? So, okay. Keeping that in mind, let's do some investigation. We know that the radius of O is 13, so I'm going to go ahead and say that PO is 13. And if I know that PQ is 5, okay, and I know that I'm looking for the line, the segment that is perpendicular to PQ, and we know that if the segment is perpendicular to a chord, then it cuts it in equal half. What would PR be? Very good. Okay, there was a bunch of talking there, but I understood what everyone said. They said it would be a 5. And then this would be a 12. Very good. So that's a 5, 12, 13 triangle. Done. Last question. Okay, now, here we got two circles with a triangle within another triangle. So the triangle ABC is isosceles, with AB being congruent to AC. They say a circle P and circle Q are in existence, and that BC is parallel to PQ. Okay? They want you to prove that circle O is congruent to circle Q. So we basically have to prove that the radii are congruent. We're looking for here is that PB is congruent to QC. So, of course, first thing, wow, that's taken long, but okay. Triangle ABC is isosceles with AB congruent to AC, and that is, of course, given. Okay? Also, we have that BC is parallel to PQ, and circle O and circle Q are in existence. That one's a given. And then for our third one, I'm sorry it's taking so long today. Okay, could you do side splitter is the question. You could do side splitter if B and C were the bisectors of AQ and AP. But from what I have already, knowing that BC is parallel to PQ, I already know that AB is congruent to AC, but I also know that angle ABC is congruent to angle P. And I know that ACB is congruent to angle Q, right? Right? Because if parallel lines, then corresponding angles are congruent. Okay? Almost done. Now, step 4. I've got that angle ABC is congruent to angle ACD. I have ABC is congruent to ACB. Why? Why would angle ABC be congruent? Not isosceles, but it is isosceles, but it's if sides, then angles. Okay, so now I know that my next reason is going to be transitive. What can I prove here to be congruent to itself to use the transitive property? PQ? Very good, son. P is congruent to Q because of the transitive property. No, it's not substitution. If ABC is congruent to P, and ACB is congruent to Q, and ABC is congruent to ACB, then P is congruent to Q because of transitive. If you put substitution for this one, I could accept that, yes. Now, AP is congruent to AQ now. Also, because if sides, that actually, this would be if angles, then sides. Then very good. I heard someone say subtraction. Very good. PB is congruent to CQ. PB is congruent to CQ because of the subtraction property. Since AB is congruent to AC, and that's part of AP and AQ, I subtract those. PB must be congruent to CQ. And last but not least, circle O is congruent to circle Q because the radii are congruent. Circles with congruent radii are congruent. Thank you very much. God bless you and have a great day.